It's with great pleasure that I now turn this special session over to Jan to begin. Jan, take it away.
Thank you, Chris, for this introduction. Good evening, afternoon, everybody. Today I would like to give you an update on the solutions that we have for vital sign monitoring within analog devices. Looking to the agenda, first of all, I would like to give you a short introduction about vital sign monitor solutions as such. After this, we will go into the technologies for vital signs monitoring, and from that I will drive you through the different subsystems in terms of biopotential measurement, optical measurement, bioimpedance measurement, and some more details about motion sensing. After this, we will have the Q&A. Why do we have to monitor vital parameters? Vital parameters are very important to give feedback on the certain condition of a person or a patient. Assume that someone from an accident is being brought to a hospital. Physicians, first of all, they want to measure what the vital parameters of persons are or patients are. What is important, of course, is heart rate, but also next to heart rate, blood pressure, temperature and respiration is being measured. Vital parameters also are being measured and observed while giving treatment to patients. So when you give a medication, you want to see very closely if the vital parameters of the patient are moving towards the direction that you expect them. So assume that someone has a temperature of 40 C and you give the medication. You closely want to look also if the medication is supporting the customer. Next to vital parameters that are being monitored in hospitals, we see also that there is a lot of interest from people, while doing their exercising. So there is more and more interest in personal monitoring these kind of parameters. So that market actually, is helping us a lot, where we see also these kind of applications moving outside the hospitals. So the trends in measuring vital parameters is that initially these kind of monitoring systems were being used in hospitals only. What you see that from clinical VSM applications, there are different parameters being measured, including ECG, oxygen saturation, what is also called SpO2, CO2, respiration, temperature, and blood pressure. From the clinical applications, we see also that physicians are using systems for telemetry, meaning that, for instance, someone with a cardiac disease or potential cardiac disease is being sent home, and that those kind of parameters like heart rate or SpO2 are being measured for a certain period of time. The new market, what we see happening now, is that sports and wellness is popping up, and this is a growing market. So this started back 5 years, and looking into these use cases, we see that parameters like heart rate monitoring, step counting, motion profiling, but also skin temperature and skin impedance are being monitored. While looking into this market, we see that clinical VSM is mainly being done inside hospitals, where sports and wellness, of course, is more an out of hospital use case. The telemetry systems as such, this is something that we have seen using inside hospitals, but also outside. Moving forward, we see that the market is changing. First of all, is that clinical VSM is moving outside hospitals and also moving into the area of rescuers and, let's say, more the professional applications and semi-professional. But we see also that developers of sports and wellness systems are more interested, to get more value more money for their products. So they move up the ladder towards the semi-medical applications. So there is a lot of activity ongoing in wearable VSM applications like ECG monitoring, heart rate monitoring, respiration, SpO2, but more in a semi-professional area, moving into wearable devices and patches. Vital signs monitoring is actually being used everywhere. So looking to this market, the medical industry, was in the past was actually the only area where vital signs were being monitored. But after the sports and wellness market, we see now also that other industries have interest in monitoring vital parameters. Automotive is one of those. So there is a lot of interest these days from the automotive industry to monitor the vital parameters of the driver. And on a car, you can control everything, except the driver. So if there is a certain event happening, or you can detect when a driver, starts to get tired, and might fall asleep. You can monitor this, for instance, by the heart rate that could go down. And based on that, you can take action, either to try to wake up the driver or to brake the car. The other market is security. There's a lot of interest from the security market in monitoring vital parameters of persons. First of all, for prediction, so when a certain disease might happen. The earlier you can detect that a disease could happen, the faster you can start to react on that and try to prevent the body from having additional damage. Also, we see the security market being interested in using vital parameters as authentication to detect if this is indeed the person that you are expecting to be on the laptop, for instance. Another market is assisted living. There's a lot these days on an aging population. You have a lot of people these days that live alone. So if you can support those people by monitoring their activity, maybe from remote detect when there is a fall, so you can support those people and you can improve actually the quality of elderly people that are living alone. So vital parameters these days are monitored in a lot of different use cases. What technologies do we require to measure wearable vital sign monitoring? In fact, there are different technologies that are needed. First of all, you need to monitor, of course, the vital parameters themselves. What could be heart rate, or could be your oxygen saturation level, or could be your body temperature. Besides the vital signs, you need also other use cases. And first of all, that is activity tracking. And why is activity tracking so important? If you measure a vital parameter like a heart rate, and the heart rate is 140, it doesn't say anything unless you know what the person is doing. If you have a heart rate of 140 while you are in bed and sleeping, that is a bad sign. A heart rate of 140 while taking a jog, that will be fine. So always we see that vital parameter tracking is being done in relation also to motion. Next to motion sensing, also body composition could be part of a vital sign monitoring. So body composition means how much body fat do we have versus bone and muscle, for instance. And the other use case could be stress level detection. There's a lot of interest these days in monitoring stress. For each of the different use cases here, you need the technology behind this, and which is support that. So in terms of motion sensing, ADI supports MEMS technology. For body composition, you could make use of impedance monitoring. Stress level can be done either by impedance monitoring, since when people get stressed, you see that skin impedance is going to change. But also you could make use of an optical measurement technology. And optical means that you're more focused on the heart rate, but also heart rate variability when it comes to stress level monitoring. And the last use case is for vital sign monitoring, like ECG monitoring, is biopotential technology. You see that we have circles around each of the technologies. So in the following slides, I would like to share some more details about the solutions that Anarogrodevices has available to support those measurements. Biopotential measurement. What is biopotential measurement? In fact, biopattern is that you monitor the activity of the heart. So at the moment that the heart starts to beat, you will be able to measure very small signals at the skin surface, what we call electrocardiogram or electrocardiography. So when the heart starts to beat, you have a signal, what you can see on the slide, that's built out of a P wave, a QRS and a T wave. At the moment that the atrium compress and press the blood into the ventricles, you have a small signal, what we can see as a P wave. And after this P wave, the event happens that the ventricles actually compress and push the blood out of the heart into the body, into your cardiac system. And that's actually in a bigger peak called QRS complex, what is a few millivolts, so it's a very tiny signal. And then after this, a T wave will follow, what actually makes the heart prepare for the next heartbeat. On measuring ECG, there are certain requirements. First of all, the bandwidth, within you would like to capture the ECG signal. That bandwidth is somewhat from close to DC up to 150 Hertz. And depending on the use case, you could make that bandwidth a little bit wider or a little bit smaller, but this is more or less, the common frequency band you're measuring in. The amplitude is something around, 1 to 10 millivolts. And the noise levels that you were measuring against is somewhat about 10 microvolts peak to peak. So when you have two electrodes in a single lead ECG system, you have those electrodes connected to an analog front end. And if you look to the signals that you're looking at, the ECG signals, they are very tiny. And those are surrounded by a lot of interference. So first of all, on the plot you see at the left side you see a big interferer, what is actually the DC offset. And the DC offset is caused by the electrodes which are attached to the chest or to the human body. So that's a big interferer. If you look a little bit further down in the frequency response, we have 50-60 Hertz main frequency what will interfere your measurement. And next to that you might have also other interferers like a pace detector, AC signals that you inject in your system for lead-off detection. So actually these are all signals which are interfering your ECG system signal where you have your interest in. So the analog front end needs actually to amplify the ECG signal and suppress all the interferers. And that's actually what the front end does, that analog device is designed. 8233 is a single lead ECG front end. Looking into the block diagram of the device, you see that we have three electrodes or three connections to the human body. So we have the two electrodes which are measuring across the heart to capture the ECG signal, and there is a signal that goes back to the foot, the right leg drive as we call it, what actually drives the common mode voltage of that patient or person. So what you would like to do is that your analog front end is on the same common mode level as the person itself. The 8233 is a front end that is built around an input signal stage, what is actually an instrumentation amplifier, followed by a second stage. The input stage is divided in two different stages. So there is a limited gain at the input, and after this gain we have a high pass filter. And this high pass filter is included to reject the DC offset from the electrodes. And directly after that high pass filter there's an additional gain stage where the total gain of the input amplifier is up to 100 volts per volt. After the input stage there's a second stage what includes a low pass filter. So this is a third order low pass filter, and that filter is included to reject all EMG signals. So signals that in fact are coming from motion activity. The output of this 8233 is an analog output. And the reason for not integrating the A to D converter is that we would like to be flexible. And usually if you have this analog front end, it's connected to a processor anyway. So why not taking a processor with an onboard A to D converter? What gives you additional freedom in additional filtering between the analog front end and the A to D converter with the processor. The chip is in a tiny package, so it's 2 by 1.7 millimeters, so very small and in particular designed for low power applications such as fitness monitors, portable systems, so portable ECG systems, but actually any cardiac system that requires electrocardiography could make use of this 8233. The device is consuming 50 microamps, so it's also very low power to be able to run this for a long period of time of a coin cell battery. Including this 8233 in your system has a lot of flexibility. And first of all, you need to look into the use case of your application. When people have interest to include this in just a heart rate monitor, you have only interest to detect the QRS, so the pulse when the heart actually compresses and press the blood into your cardiac system. So what you need to do is limit the bandwidth. So the wider you're going to measure, the more noise you integrate in your system. So in a sports band application, we recommend the user to have a frequency band from 7 to 25 Hertz. And the high pass and low pass filter cutoff can be set by capacitors and resistors. For a monitor application where people have interest in a more detailed look at the ECG waveform, we recommend a bandwidth from 0.5 to 40 Hz. And in case people have more a diagnostic system, you take the entire frequency band from 0.05 Hz up to 150 Hz. And all those cutoff frequencies, corner frequencies, can be set by the discrete resistors and capacitors. On the slide you see also that we have a software tool available which can be downloaded from the web, what helps you to very easily configure the system yourself. So it gives you also the behavior and the phase margin that you design against. An additional feature in this analog front end is a fast restore mode. While you have this ECG front end, for instance, integrated in an exercise machine, and you take the two electrodes, the filters need to settle, and this could take up to seconds, what is sometimes annoying in the application. So what we developed integrated was a system where we have additional switches to change the filter response. So at the moment that the system detects that one of the electrodes is coming off, it switches the switches in such a situation that once you take on the electrodes again, it settles very fast. And after complete settling, and catching up the heart rate signal, it changes the switch mode into the different filter action to improve your overall performance. So that's a handy feature that is embedded in this analog front end, but otherwise is difficult to integrate in a discrete system. So the 8233 is something in full production and being used already in a lot of systems that are available as a final product on the market. And we move now to the second topic, optical measurement. Analog devices is for a long period of time already involved in optical measurement, and we have a long history from the time that we were still focusing on communication for laser drivers, etc. Now this technology is being used for different use cases, and vital signs monitoring is one of those. While using vital signs by optical technology, we make use of PPG monitoring. So PPG stands for photoplasmography. And in fact, what you do is injecting certain light into the human body or the tissue, and you measure the response. either by a transmissive measurement or by a reflective measurement. And you might know the classical systems of oxygen saturation. So when you go to the hospital, you get the finger clip, where light is being sent into the finger, and at the opposite side you have a photodiode to measure the absorption of the light, or actually the light that's sent through the finger. These days we see more and more interest from customers moving from a transmissive system into a reflective system. And not as since reflective is better. Usually what we see is that in a transmissive measurement technology, the signal strength is much bigger, but the reflective technology is more handy. So what you can do is make the sensor, for instance, integrated in a wrist-worn device. So you don't have something that is sending light through, a certain part of the body, but you measure actually light on the emitter and the receiver at the same site. What is easier from a mechanical perspective. While you do the measurement, you will see, of course, an DC component from the light coming back, and on that there's an AC component. And the AC component is actually a measurement for the blood flow that you see that is traveling through your veins, and that's actually what the PPG signalers look like. So you have a top. And then you have a small, reflective point, and when you go down to the bottom of the waveform, and actually the signal what you see here gives you also some feedback about the cardiac age of the system itself. So the stiffer your cardiac system gets, the less reflection that you will monitor. So PPG monitoring can also be used for cardiac age detection. What with PPG technology is being used in oxygen saturation. For oxygen saturation, you need actually two waveforms and two wavelengths. And the reason for this is that you are going to measure the amount of oxygenated hemoglobin versus the total amount of hemoglobin. So the SpO2 signal that you get back is a certain percentage. And the reason for having two wavelengths is that oxygenated hemoglobin will absorb more infrared light compared to red light. So if you have actually two wavelengths, you can make a calculation after that what the percentage of oxygen is attached to the hemoglobin in your system. In an optical system, you have need for several building blocks. So first of all, you need light being sent into the body, what we are doing with LEDs. You need a receiver, what is in this circuit diagram, the photodiode, and then you need your signal conditioning block. Depending on the use case, you might have just one wavelength of light, two or three. In the application, in the use case that you see here on this slide, we have green light for heart rate, and we have red and infrared for SpO2 monitoring. The photodiode is interfaced to an analog front end, followed by an A to D converter, and you see also that we have the LED control, what is being driven out of the same analog front end. Looking to what analog devices can offer in this signal chain is that we have complete integrated photo sensors. And those photo sensors have been developed by a photodiode followed by a current-to-current amplifier, so very, very low noise. It's not always needed that you have in an optical system those kind of photo sensors integrated, but in case you would like to measure, for instance, SpO2, so oxygen saturation, you need a much higher signal-to-noise compared to just optical heart rate. And for those use cases, an additional photo sensor with an embedded amplifier might be of benefit for you. We have also the complete analog front end integrated in a subsystem. And that's actually the ADPD 10X or the 10-8X family. And the front ends that we have available are built around a transimpedance amplifier, followed by a signal conditioning block, A to D converter, and also integrated LED drivers. And for those people that would like to have a complete system where we have everything integrated from electronics up to all the optical devices like the LEDs and the photodiodes, Analog Devices supports a family of optical modules which can be found under the ADPD 14, 17 and 18X family. While designing an optical system, there are certain issues that you need to take in consideration. So first of all, the interference of ambient light is something what could destroy your measurement very easily. So if you are going to design a system like this, you need to make sure that you are that you can reject ambient light interference. And usually, if you have ambient light coming from the sun, that's something easy to cancel out, since the sunlight is DC. So if you have a small filter, you can completely reject the light coming from the sun. But assuming that you have an optical system being used inside a building and you have solid state lighting like the LEDs, which are switching at 50 kilowatts, that's much tougher to reject. The reason that we did several integrated front ends for optical measurement is that we were also capable of integrating the complete ambient light rejection. So looking to the front ends that we have available, we have a two-stage ambient light rejection building block that makes it very robust against interference coming from the outside. When you start to design an optical system, motion is also an interferer that could give you a lot of artifacts. When you have, assuming you have a device which is being worn on the wrist, and you start to measuring your optical heart rate while you do a job. So you're moving your hands, and the pace of moving your hands could be exactly in the range of your heartbeat. So you need to compensate for that. You can compensate, of course, by mechanics, making, for instance, a strap which puts the device very tight, to the skin. That is partly helping you to prevent artifacts coming from motion. But what we also do is that we integrate motion sensors, or recommend to integrate motion sensors. And the ADXL 362 is a very good part for that. So while we monitor the optical response, we monitor also motion in 3 axes, and we compensate for that with an algorithm. Also, for an optical system, you need to take in consideration the physiology of the human body. It's very important that you monitor, that you look carefully where you have the sensor being placed on the body, and the position on the body could help you to improve the overall signal response. You can do heart rate on the wrist, and that's one of the use cases that we see a lot. But if you have an heart rate monitor integrated in a wrist-worn device, usually you have your optical system, facing the top of the wrist, where you have a lot of bone. And if you have a lot of bone, it doesn't make sense to have a light that penetrates very deep into the tissue, since then you hit the bone anyway. So that is the reason, for instance, why we are recommending a green wavelength of LED light, which penetrates very little into the tissue. So actually, what you do is measuring the scattering of the light, from the skin itself. On the other hand, if you have people with a colored skin, like the darker skin, they usually have much more pigmentation, and with that you need a different light source that penetrate better into the tissue. So we see in those kind of use cases that usually red or infrared LED light will give you a better response. So depending on the color of the skin, but also the position, it might be that one wavelength will do a better job compared to the other one. That's what you also need to take in consideration. And then last but not least, if you have a system, mechanical aspects are very important. So if you have a mechanical system and you have a photodiode, the distance between the LEDs towards the photodiode are very important. Light that penetrates deep into the tissue usually have also the need for a wider spacing between photodiodes and the LED. So that's something you need also to look carefully into before you start to design an optical system. In some circumstances, also that the spacing is very important, since it might be, if the spacing is very tight to each other, that you get a DC offset coming from light that doesn't penetrate the tissue, but comes from the LED straight on the photodiode, what ends up as a DC offset, and this will limit you in the dynamic range of the A to D converter. So these are all kind of aspects that you need to look careful into before you design an optical system. In terms of the analog front ends that analog devices developed for these kind of use cases, we have now actually 3 generations on the market. I'm not talking about the first generation, but the second generation that came to the market was the ADPD 105, 106, 107. It's actually an optical front end that has 4 signal chains, so you can actually connect that front end to 4 different photodiodes. Integrated also with 3 current sources, so you can drive 3 different wavelengths of LEDs. The system has a superb ambient light rejection block embedded, so helps you to overcome the challenges that we discussed in the previous slide. And we have different flavors available, so devices with I2C interfaces, but also SPI in case the customer would like to include an SPI interface. There are also additional opportunities with these devices, so you do not necessarily have to use them in an optical system, but also the inputs can be used to measure other sensor signals. So there is a lot of flexibility integrated in the ADPD 10X family. After the 10X family, the 1080 family came to the market, which was released in February of this year, where we improved the device in terms of signal-to-noise ratio. So either you can improve your signal-to-noise by having the same power dissipation compared to the previous family, or you can stay at the same signal-to-noise ratio as the previous family, but then you have a benefit in power dissipation. So in fact, you have a longer battery lifetime. So both standalone front ends are available and can be used for new designs. So while you build and design an optical system, there are different ways of moving forward. So either you can take a discrete solution with an analog front end that we just discussed, or you could move more to an integrated module. The selection that really depends on the knowledge that the customer has. So if you take a discrete solution, you have all flexibility in terms of the mechanical design, the spacing between the photodiodes and the LEDs, the colors of the LED wavelengths that you are using, but also the size of the photodiode. If you take a bigger photodiode, your response will be much more, the SNR performance could be much better. However, you might be also picking up more ambient light. So these are all kind of considerations that you need to take into account. Also, if you have a discrete solution, you could add additional plastics like filters or like lenses to improve the overall signal response. But you really need to know what you are doing. So not every electronic engineer is an optical engineer. And usually we recommend the customer to look into this if they have the knowledge, or if it would be not easier to move forward with a module. So to make life easier for designers which are not optical experts, we developed a complete family of optical modules. So the modules that we have available have different LEDs integrated. It helps you speeding up your design, and time to market is important. The module also could do a good job for you. Different 2 families which I would have a close look into, and that's the ADPD 174 and the ADPD 188. The 174 was the pre-successor after the latest one we introduced, and in fact that device has the photodiodes, 2 green LEDs and a red LED integrated in the package. If you look to the slide at the left on the corner, you see some simulation models about the light that we are sending through a glass window into the tissue. And you see actually that with light that's being sent, there is no light coming back to the photosensor when there is no tissue attached to the sensor. What means that there is very little optical crosstalk. And that's one of the challenges that you have to design against if you have a plastic window on top of the sensor. The ADPD-188, that's a new sensor that we actually, well, we changed a little bit the setup of the photodiode. So the photodiode has been rotated by 90 degrees to have a better response towards the light that's coming from the LEDs. So it has two green LEDs integrated, and this SNR performance versus power is 3 to 6 times better compared to the pre-successor, what it was the ADPD-174. So in case you would like to move forward by designing an optical system for heart rate, the 188 is the device to look after. On this slide you will see in more detail the ADPD-188, and if we look to the block diagram you see that we have the LEDs and the photodiodes integrated, followed by a switch matrix and a transimpedance amplifier with some more signal conditioning. There is a two-stage ambient light rejection block, a bandpass filter to reject DC light, followed by an integrator, and with that we make use of synchronous demodulation. So we control very carefully the receive part versus the LED drive. And with that we can reject AC ambient light up to 100 kilowatts very, very nicely. The ADPD-188 has two green LEDs and one infrared LED. And the infrared LED mainly is being used to detect when the device is approaching the skin. So when you put a device on, that infrared LED could be used to wake up your complete application. So it could be used like like a switch to start driving the green LEDs. We are recommending this device in different applications for heart rate monitoring, heart rate variability, and SpO2. That in that use case, this device also could be used. However, then you need to have additional LEDs. But the nice thing on this device is that you do not necessarily have to need the integrated LEDs, but you can drive also external ones. So that means that in a reflective optical system, the ADPD-188 can be used, but even also if you would like to measure more in a transmissive mode, you have the ability to drive external LEDs from this device as well. You see a complete overview of the family. So we have half dozen different devices. So we have 3 analog front ends, but you see on the slide also 6 different integrated modules with different wavelengths of LEDs, with different sizes of photodiodes, and depending on the use case, being either heart rate or heart rate variability monitoring or SpO2, you could take one or the other devices out of our family. So I included this slide just for your reference. The case where we see a lot of interest is on monitoring blood pressure. And then blood pressure in a non-invasive way. And this technology, for measuring non-invasive blood pressure, we could make use of pulse transmit time. And that means that at the moment that your heart contracts, the blood is being pushed from your heart into your cardiac system. There is a certain delay, that the blood pulse is arriving in your wrist. And there are algorithms developed to retrieve your blood pressure based on your sex or your age. That gives you a measurement for your blood pressure. So what you need to do is to detect carefully the moment that the heart contracts, and in relation to that you measure also the time that the pulse is arriving in the wrist. So what you need to do is to synchronize an ECG measurement together with an optical PPG measurement. And the ADPD-188, for instance, but also the other ADPD families devices can support this use case. So what you do is that you have your front end, your optical front end. You connect the LEDs, or in case you have a module, the LEDs and the photodiode are embedded. But on an auxiliary input, you take the output of our ECG front end. And the only thing you need to do is take the output, what is the voltage of the ECG front end, and convert this back into a current by a series resistor. And with that you have an ideal system which is very nicely synchronized to measure the delay from the contraction of the heart towards the pulse what is arriving at the wrist. So we support in this an 8233 plus ADPD 1XX. In case you would like to evaluate one or more of our optical devices, we have evaluation boards. So you see here some of our device boards available, what includes an optical sensor plus a motion sensor. And the reason that all those evaluation boards have the motion sensor integrated is that optical measurement is very sensitive to motion. So moving forward, you have here the complete solution already available that could help you to measure optical response with synchronized motion detection. Those devices, they connect to an interface board, what is called the eval ADPD UCZ, but we have also a more generic board available. So in case you would like to play with the LEDs and the photodiodes, the generic boards might be more appealing to you towards the complete system that we have embedded based around a device board with an interface board. So those are available. So from this, I would like to move to the third topic, being bioimpedance monitoring. And for bioimpedance monitoring is used in a lot of different scenarios. And I'm summarizing the different use cases that have needs, for bioimpedance measurement. So first of all, impedance monitoring can be used for EDA or GSR. EDA stands for electrodermal activity, or GSR for galvanic skin response. And these measurement technologies can help you to detect stress. At the moment people get stressed, we see that the skin impedance is going to change, and that's what we can detect by this. For measuring skin impedance, you need to stay actually at the top of the skin, and we can do this by excitating the measurement by a DC current or a very low frequency. The higher the frequency gets, the deeper you penetrate into the tissue. So usually for stress monitoring, we use something like 10 Hertz. In case you're going to increase the excitation frequency, you go more inside the body, and we can use that for body impedance analysis. At the moment that a body contains very little body fat, we see that the impedance is becoming higher. So we can use this technology for discriminating, for instance, the amount, or measuring the amount of body fat versus body muscle and bone. And then the third use case, what we see also, is hydration or dehydration. And with that, even you go higher with the excitation, and up to 200 kilohertz. And by that we go through the cell structure and the intracell fluids, and we can have a measurement, and reading out of how much water is the body still containing. What is a use case what is very interesting for elderly care, for instance, since older people don't tend to drink enough, and this measurement can help them to prevent from dehydration. Thermal activity or galvanic skin response in relation to stress monitoring is very important. Why is that important? Of course, nobody wants to be stressed, but if people have stress more continuously, it could finally work out in certain diseases, and diabetes, heart problems, even cancer, could be a result of being for a long period of time under stress. So there's a lot of interest in monitoring the stress levels, by personal interest from people, but also by companies, their co-workers working in a stressful environment, that they actually can monitor what the stress level is. And at the moment that level becomes too high, you can actually tell them to take a rest, or take a break, And that's why we see a lot of interest in monitoring this. What we need for stress monitoring is an AC signal, what you drive into the skin, and a receive signal. As I mentioned, usually you can measure it, from DC, but usually you don't want to do that since you polarize the electrode. It's bad for the skin. So you take a very little frequency, let's 10 to 100 hertz. You inject that sinusoid signal into the tissue, and by a receive signal you measure back the impedance. And usually you measure in the range of microsiemens. And that impedance response is very flat until people get stressed. Then you see that the impedance is going to change, but you see also much more noise on the measurement. So that measurement can be done by the front ends that analog devices have designed. For body, you need, as mentioned, a high excitation frequency to go actually through the body. You can do a body impedance measurement either from hand to hand, but you have also weight scales where you have metal plates where you measure actually through the legs. But there are also technologies available that you measure, for instance, from one of the limbs to the other one, so from hand to foot, for instance. Application like body impedance monitoring, you need 4 wires. So in this kind of measurements, you have interest in an absolute value, where in a stress monitor application, there is more interest in relative measurement. So you have interest in the change of the impedance. So for absolute measurement, you need a 4-wire measurement system where we have here the ADU-CM350 as a circuit diagram. So you see that we have an unknown Z, what in this situation is a person, and we have connected this person through our system by an AC coupling. So we have capacitors in the wires to prevent DC currents from flowing through the body. And that's required to meet the IEC 60601 standardization. In this ADU-CM350, there is a sine wave generator that pushes the current through the person. We measure the response with a transimpedance amplifier, and over the impedance we measure with an additional amplifier the voltage drop. And then the ADU-M350 has a DFT engine that out of the current and the voltage calculates your amplitude and your phase. So in fact you have your complete complex impedance. The device is very accurate and could be used for a lot of different use cases, including body impedance. So this last topic, and that's the motion sensing. And as I told you in the beginning of the presentation, motion sensing is very important since you can measure any vital parameter, but if you do not have a sense of what a person is doing or how much motion that you are detecting, the reading from an optical or an ECG signal more or less is useless. Analog devices has a long of sensing, so by micro electromechanical systems. And that MEMS technology actually is silicon, is processed with silicon. So you have moving silicon, what is making use of a capacitive monitoring. And in the classical medical applications, MEMS sensors were being used in systems like control for prosthesis. But also we have MEMS sensors integrated in an AED. To support the user, of the AED. So first of all, you need to make sure that you do not fire when a certain person is still, alive and moving. So you want to monitor very carefully if there is movement on the body, but also you want to monitor the movement on the body, since it might be that the patient or the person, that had a cardiac arrest is not moving, but that he's still, being touched by a rescuer. And so those systems have MEMS sensors integrated to measure completely silence before they start to fire the system. And then the third use case could be in a blood pressure monitor, where you measure actually if the hand, where the cuff is being placed, if that is at the same elevation as the heart. So besides these kind of classical medical applications for MEMS technology, we see now also a lot of use cases for the wearables. And first of all, it's for tracking activity or motion profiling. So if someone is he jogging, is he walking, is he cycling? So that's where those MEMS sensors are being used for. But also for rejection the artifacts, as I mentioned before, in an optical system. Other use cases can be step counting. That's actually in relation to calorie burn, but also a fall detector. It's very broadly being used in this industry, especially for elderly care. So our sensors are being used also in these kind of use cases. XL362 is the lowest power-consuming MEMS sensor in the industry. That device is actually a 3-axis MEMS sensor with a digital interface. So we have an I2C interface that gives you all the data of 3 axes. And depending on the data output rate per sensor, we can scale the power dissipation of the sensor. In full operation with an output data rate of 400 Hz per axis, this device is consuming only 3 microamps. But if you scale that down to, let's say, 100 Hz per axis, the power scales down to 1.5 microamps, so you can there have some additional saving. A nice feature that the ADXL362 has also embedded is a motion wake-up sensor. So at the moment that you drive this sensor directly from your battery, it could be used to wake up your complete application. And in that mode, we drive down the sampling rate of the A to D converter to only 6 Hz. So every 150 milliseconds, we wake up the sensor, we monitor the motion and the time of the motion, and what you actually can also control by writing threshold levels to the sensor. And if it wakes up and it doesn't see the motion, towards the threshold level that you programmed, it goes in the power down mode again. And at the moment it wakes up again, it says, oh, I've seen 300 millig at 500 milliseconds. Then it can generate an interrupt and to wake up your overall processor and application. And in this mode, this sensor is not consuming more than 300 nanoamps. So we can use that also for a long period of time, from a single battery charge or from a coin cell battery. So that's the ADXL362. What we see a lot with in combination with optical sensors and with ECG monitors. So that brings last slide. So in fact, we can be your one-stop shop. So we have a wearable developed that integrates all those sensors. So it has a motion sensor combined with PPG sensors for optical measurement, with an ECG front end, a solution for impedance monitoring, everything integrated in a wearable device. The reason for many layer devices for doing this is to support customers which are developing algorithms. Those people usually they want to measure different parameters, and from that hopefully they come up with new use cases. And without having to start to building their own hardware, we developed a platform that can be used by those people to give them a quick start while moving forward and proceeding with writing their algorithms. Summary of what analog devices can offer you in vital sign monitoring for clinical and wearable applications. So thank you very much for watching, and I give it back now to the operator.
So Jan, our first question for you here: what are the most important considerations for designs of fitness wearables versus clinical grade devices?
Oh, that's a good question. The considerations really depends on the use case. So if you design a fitness wearable, you first of all you need to usually you measure with a lot of motion. So while you do your exercise, there is motion. So those kind of systems need to be designed with integrated motion sensors, but also the algorithms need to support this. When we look to a clinical grade device, usually you have much more flexibility on what technology you're using. Assuming that you want to measure heart rate monitoring or heart rate variability, you can do this by optical, but also by ECG monitoring. And ECG monitoring means that you can connect electrodes to a body. And with that, you look a little bit less to the comfort, which is very important in a fitness application, but you look more, to the accuracy of the reading itself. So first of all, you need to look, okay, where is the sensor being placed, and from that, the technology that is available to you can, decide, how to move forward.
All right, thank you, Jan. We have another question here for you. It says there are many new companies entering into the vital signs monitoring. What is still driving the industry?
Oh, that's another good one. Indeed, there are a lot of companies these days, they jumped on this train by, seeing that bubble, on wearable monitoring, etc. And heart rate and motion, so pedometer applications, I think, that market already, has been fulfilled. There are a lot of suppliers that make very low-cost wearables to support those use cases. But next to these use cases, there are still, I think, a lot of opportunities. There are people which have interest to measure, for instance, their blood pressure, but more in a continuous way. So you can, of course, take a device with a cuff-based system. You need, to pump up the cuff, and you have a single measurement. But what if you have a blood pressure monitor that measures 24/7? That would be great. Another application, for instance, is on glucose monitoring. So people with a diabetes disease, they measure now and then, a couple times per day, their blood glucose level. But life for those people would be much easier and much more comfortable if they have an automatic system that measures their blood glucose level, and depending on the level, automatically injects, insulin. So I still think that, based on what the capabilities are, there are a lot of opportunities for newcomers into this market to make a device what doesn't exist today. So there is still room for growth.
All right, thank you, Jan. Looks like we have time for just one more question here. It says, can this technology be incorporated into clothes, for example, textile-based VSM?
Absolutely. So we talk about smart wearables or smart watches where we have the sensors integrated. But the next step is that people want to make other smart devices. And you have smart devices like shoes where we have an MEMS sensor integrated, what is able to measure the steps, what is able to measure the distance of the steps or the distance. But you see also that with that you can, for instance, measure very precisely the pressure on the sole. Next to shoes, there is a logical step that people are starting to measure ECG waveforms from textiles. And in the past you had the chest strap, what everyone knows, what is very uncomfortable while going outside, and doing a run. But if you take conducting wires which you weave into the shirt, you can make textile that has the embedded electrodes to make an ECG monitoring system possible. And the value add that you see there is that measuring heart rate by ECG gives you a better performance compared to measuring heart rate from optical. So for sure this is possible, and there are also companies working on this.
All right. Well, thank you, Jan. That is all the time that we have for questions for today. Once again, if we didn't get to your question today, someone will get back to you after the program is over. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank you for attending today's webinar, Technologies for Wearable and Clinical Vital Signs Monitoring, brought to you by Tech Online, Analog Devices, and Arrow. This webinar is copyright 2018 by Aspen Core. The presentation materials are owned by or copyright by Tech Online, Analog Devices, and Arrow, and the individual speaker is solely responsible for his content and opinions. On behalf of our guest, Analog Devices, and Arrow, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.